Hello and welcome to another awkward yet thought-provoking, life-changing, maybe even virtual lesson with Mr. Kuiper. We are going to be looking at 8.1 today, and there's actually a lot packed in here, so I want to make sure that we do this and do this well. We're starting a new unit, and if you notice on the top of your note page, the title of this unit is Similarity, and what we're going to be looking at are figures, different polygons that are similar to one another. And mathematically speaking, what it means to be similar is very, very much what it means just in normal speak, right? If two things are similar, that means they're not exactly the same, but they have a lot of the same attributes, a lot of the same qualities, so that we would call them similar. And the same thing is true in math, and we're going to dive into that a little bit today. Okay, this first box right up here has a lot of really good and important information in terms of similarity and in terms of kind of the nitty-gritty details that we're going to dive into. So I do want to take a look at this, and I'm going to highlight a few things from this box because, like I said, there's a lot packed in here. Okay, the first thing that it mentions is actually this word similar. And mathematically, what you can think of for similarity, or for two shapes to be similar, okay, they have to have the same shape. The shape is exactly the same, but it might just come in different size. Okay, we have actually seen an example of similar figures in the first semester when we looked at dilations. A dilation is just increasing or decreasing the size of something. I like to compare it to when you have an image on your computer, you can kind of click the corner, and when you click the corner of that image, you can scale it up or down proportionally. And all you're doing when you do that is just creating similar figures by making it bigger or making it smaller. Okay. So when you make it bigger and you make it smaller, there's a mathy word for that, and the mathy word for that is scale factor. Okay, that's kind of hiding here in the second to last sentence. Basically, what a scale factor is just the number that you're multiplying by. So if a figure is 2 times as big as one that is similar to it, then the scale factor would be 2. If a figure is 5 times bigger, then you would say that the scale factor is 5. But order does matter, because if you go from this smaller one to this bigger one, let's just say it's twice as big, we would say the scale factor is 2. From here to here, the scale factor is 2. Okay, so we have this scale factor, and they label it with the letter K. So you have A, B, C for your side lengths over here, and then now each of these are being multiplied by K, or your scale factor of K, which if it was twice as big, then this would be a 2. Okay. But notice if you go from this one to this one, from the bigger one to the smaller one, your scale factor would no longer be 2. I'm not taking each of these sides, doubling it, and getting this side. I'm actually cutting each of these in half. So order does matter, and we'll see that here in just a little bit. But scale factor is just fancy for the number that you're multiplying by to go from one figure to its similar figure. And the ratios, if you remember ratios from first semester, then just algebra, you work a lot with ratios. The ratios of each of the sides will also simplify into that scale factor as well. Okay, so that's kind of some of the components in here that make it similar. The other component that we want to focus on as well is that the corresponding angles are going to be congruent. So what you have here is that corresponding angles will be congruent. So the angle measures don't change, which you should hopefully remember from when we did dilations first semester. The angle measures stay exactly the same. So the bottom right angle here is A, the bottom right angle here is D, so angle A and angle D are congruent. So those corresponding angles are congruent, and the corresponding side lengths are proportional. And each of those fractions, those proportions, will simplify into the scale factor. Okay. Hi. Are you done, or do you have questions? Okay.
Like on this, I wasn't ready for that. But
Okay. Thank you. If you know Hayden Zimmerman, you can give him a hard time for interrupting your riveting geometry lesson. How dare he? But anyways, I don't know where we were, but last thought on similar figures is there is notation for it, and the notation for something to be similar is this little squiggle. So if you see that squiggle between two figures, then it is telling you that they are similar. Okay? So we'll do a couple examples, and hopefully this will make a little bit more sense as we get rolling with this. Okay? So in example 1 here, it says that triangle RST, and there's that symbol that I just referred to, is similar to XYZ. That's how you would read that. Triangle RST is similar to triangle XYZ. So their sides are going to be proportional, and the angles will be corresponding angles will be exactly the same. So in letter A, we're finding the scale factor from RST to XYZ. So the order matters here. I'm going from RST to XYZ. So I'm going from the bigger one to the smaller one. And since I'm going from bigger to smaller, what that means is my bigger figure is shrinking down. So since it's shrinking down, my scale factor has to be smaller than 1. Because when you multiply by something smaller than 1, you would get smaller, right? So in this case, it's like if this image was on the computer, I would click at S, and I would just shrink it down slightly, and then make this triangle at X, Y, and Z. So since I am going from this triangle to this triangle, I'm going to find a scale factor that represents what number do I multiply all of these things by to get to their corresponding sides over here, okay? And you might not be able to see that right away because these are corresponding sides, and you're like, what do I multiply 20 by to get to 12? That's not something that I'm familiar with, okay? And there's really two different ways that you can do this, okay? The first way is to solve for the scale factor directly. So you choose any proportional sides that you want. I'll just choose the bottom ones because I'm already pointing at them. So this side is 20, this side is 12. I want to know, I'm going to scale this thing down. When I scale this thing down, what am I multiplying by? So one way that you could do it is you could say, I'm taking 20, I'm multiplying by something, and I'm getting 12. I could have done that with the left sides. I could have done that with the rightmost sides. But what I'm doing is I'm just picking one pair of corresponding sides, and I'm trying to figure out, okay, what is the scale factor here? This is 20 times the scale factor, so I will divide each side by 20, and then my scale factor, which I labeled as X here, maybe more commonly the letter K, is 12 over 20, but this is a fraction that can be simplified. I can take a 4 out of each of these, and that would simplify into 3/5. So my scale factor here is equal to 3/5 if I go from the bigger one to the smaller one. Okay? So maybe that makes sense to you. Maybe you're like, okay, yep, I'm with you, got it. There's technically another way that you can do it as well, and you can look at ratios because the ratios of these sides will simplify into the scale factor. So since I am going from the bigger to the smaller, I know that my scale factor will be a smaller number, so I'll start with the smaller number, which in this case was 12 over 20. You can just do the fraction directly, and 12 over 20 simplifies into 3/5. Okay, so, and you could have, like I said, you could have done that with the 18 and the 30, the 15 and the 25 as well, and you would have gotten the same answer. Okay, so going from this one to this one, I would multiply each of the sides by 3/5. Okay, so this gets at the corresponding side lengths part of similarity. Here, the other key part of similarity is that all the angles the corresponding angles are congruent. So in this case, angle T is congruent to angle Z. Those are the top ones. The left ones have to be congruent. Angle R would be congruent to angle X, and then angle S would have to be congruent to angle Y. Okay? So those ones would have to be congruent as well. And lastly, kind of getting back at this ratio of corresponding sides again, with what a statement of proportionality means. Basically, all a proportion is just two or more fractions that are equal. So if a proportion is two or more fractions that are equal, let's just start writing what equal fractions I would have. Okay, so this over this would equal this over this, which would equal this over this. Sorry. Yeah. Yeah, I'm doing a lesson. But what's up? Do you need something from me? Yeah, I am, but that's okay. Okay. Oh, okay. Thank you. I'm a popular guy. Anyways, statement of proportionality. Proportion is just fancy for fractions being equal to each other. So what fractions are equal to each other? Well, if I look at xy over rs, which is what I did in letter A, that fraction would have to be equal to zy over ts, which would have to be equal to zx over tr. So this is just saying that the bottom side's fraction have to equal the right side's fraction, which would have to equal the left side's fraction. And all of, ooh, you can't see any of that, I'm sorry. And all of that would have simplified into the scale factor of k or x or whatever letter you choose. It doesn't really matter. But this is just getting at even further that the side lengths are proportional. Okay, and this last little note down here about corresponding side lengths in similar polygons. This is just saying not only would the side lengths be proportional, but everything else. If you were going to draw in the height or the altitude, that would be proportional. If you were to have mid-segments, those would be proportional. Medians would be proportional. So all any two corresponding side lengths would be proportional, and it would simplify into the scale factor. Okay. So we'll do a couple more examples for maybe to really hit this home here. Okay, example 2 and example 3. In the diagram, we know that the triangles are similar, and we are looking for the value of x, which is up here. Okay, so since I know that the triangles are similar, I know that the side lengths are proportional. So I know what I'm going to have to, since I'm solving for x, I know I'm going to have to use the number 30 over here, because these are the corresponding sides. Okay, so I know that since this x is in this position, 30, I'm going to have to use that. Regardless of the other numbers that I choose, I know that I'm going to have to choose this one. Okay, so what I'll do is I'll say, okay, well, this has to be proportional. If I go from left side to left side, so what I'm looking at is left side of this one to left side of this one will have to be proportional to right side over right side. So what I'm doing is I'm saying the two left sides over here, the 15 and the 18, will be proportional to, it's not the hypotenuse because we don't know it's a right angle, but the longer side over here on the right, x over 30. Okay. Now we have a proportion that we need to solve for x, and hopefully you remember that when you did this, the easiest way to solve this, or the most consistent way that you can always use, is cross multiplication. What cross multiplication says is you multiply straight across and you set it equal to each other. So 15 times 30 would have to equal 18 times x. 15 times 30 is equal to 18 times x. Okay. And when you do 15 times 30 is 450, and that's equal to 18x. Divide each side by 18. 450 divided by 18 ends up with 25. So that missing side length had to be 25. Okay. So you set up your proportion, solve with cross multiplication. That will be a common theme here as we go forward. Set up your proportion, solve with cross multiplication. Okay. So here's another one. Not only are side lengths proportional, but then altitudes are proportional as well. Altitude is a fancy math word for height. Okay, so in this case, we're finding the length of the altitude PS. So PS is this length right there that I will label with an X. Okay. And I'm going to actually, for the sake of what I think is potentially a little bit easier, is recognizing that this triangle and this triangle are the ones that we say are similar. So those are the triangles that I'm going to use. So if I look at the bottom side of each of these triangles, okay, notice that 6 and 6, so this whole bottom side is 12, and this whole bottom side has to be 16, 8 and 8. And the reason I'm going to do that is because now what I can compare is I can compare altitudes with bottom sides. Okay, so in this case, what I'll do is I'll say, okay, altitude over base, x over 12, has to be equal to altitude over base over here, which is 20 over 16. So I'm trying to stay consistent by saying altitude over base in this triangle has to be equal to altitude over base in this triangle. So this is the proportion that I have. And now when I cross multiply, I'll do 12 times 20 and set it equal to 16 times x. Okay. And when you do this, you do 12 times 20, and 12 times 20 is 240. At least it was when I was in school. I think it still is. Right. And now since you have 16 times something is equal to 240, you would end up dividing each side by 16. 240 divided by 16 is 15. So therefore that length PS, which I labeled with an X, has to be equal to 15. Okay. So these are going to be very common problems that you're going to be able to have to work with. You're going to have to set up your proportion like we did for both of these, cross multiply, and solve. Okay. Last thoughts here, and then I will stop yapping, and that is this. Okay. We're going to be comparing not only side lengths and altitudes and those things, we're also going to be comparing perimeters and areas of similar figures. Okay. The nice thing about perimeter is the easy one. And what I mean by that is the perimeters are proportional as well. So if you knew, once again, let's just say that this figure was half as big as this one. So the scale factor from here to here was 2. All the side lengths doubled would get you that new one. Then if I found the perimeter of this one, I could just double it and have the perimeter of this one. And that's kind of what it's going at here is perimeter, remember, is just fancy for adding up all the sides. So this is just fancy for perimeter. The ratio of the perimeters will be equal to the ratio of the sides, which is equal to the scale factor. Okay, so perimeter is nice. It works exactly how we want it to. Like, oh, side lengths are 3 times as big, then I'm just going to triple my perimeter. Okay. Area isn't that straightforward, but it should still make some inherent sense because when you work with areas, remember area is always in square units. So you figure out your area and it's maybe 80 centimeters squared. You figure out your area, maybe it's 30 square inches. So anytime you're working with area, there's always this concept of 2 dimensions, right? It's length times width. So you have that 2 dimensions, it's squared, excuse me. And so what that means for us is you take this scale factor, and rather than just multiplying it by the scale factor, you'd have to square it. So notice here now, here's the area. That ratio is equal to all of these ratios again, but notice here all of those ratios are being squared. So you have to square the scale factor or square the ratios first, and then you will be able to figure out your areas. Okay, so let's do one perimeter example, one area example, and then we'll be done. Okay, so in example 4, a town is building a new swimming pool. An Olympic pool is rectangular with a length of 50 meters and a width of 25. So this is the Olympic pool shown right here. The new pool is going to be similar in shape to the Olympic pool, but will have a length of 40 meters. So what we're trying to do is find the perimeter of both the Olympic pool and the new pool. Well, the perimeter of this pool right here, the Olympic pool, should be pretty easy, right? Because the perimeter of the Olympic pool doesn't really have to take any of this proportionality stuff into effect, because all you're really doing is you're just adding up all these sides, right? So you take 50 plus 50 plus 25 plus 25, and when you do that, you add all those up and you get 150 meters. So the perimeter of the Olympic pool is 150 meters. Okay. So now what we're going to do is we're going to take that number and we're going to multiply it by the scale factor to find the perimeter of the new pool. Well, the new pool is going to be smaller, so we know that the scale factor that we have is going to be less than 1 because it's getting smaller. This Olympic pool will get slightly smaller, and then that will be this town's pool. So we need to figure out what this scale factor is. And so what we're going to do is we're going to compare that the new one has a length of 40, and the Olympic one has a length of 50. So this ratio, of 40 to 50 is going to be my scale factor. And I have to be very careful. I want 40 in my numerator and 50 in my denominator because my number has to be less than 1. So my smaller number will be on the top. You want a smaller number, put the smaller number on top. If you want a bigger number, put the bigger number on top. So then you can simplify this fraction. 40 out of 50 simplifies into 4/5, or for you decimal people, 0.8. Okay. So I think at this point what might be easiest for us is to take this number, which was the perimeter of the original, and multiply it by 4/5, or multiply it by 0.8. You could do that on the calculator. You could say 150 times 0.8 and you would have your answer. And that's certainly one way that you can do it. Another way that you can do it is setting up this proportion. And so I'm going to set up a proportion only because that's a skill that we're going to be working with a lot. So perimeter of the town's pool over the perimeter of the Olympic pool has to be equal to 4/5. Okay, and once again, you can cross multiply this, and when you cross multiply this, you get a perimeter equal to 120 meters. Okay, 120. And lastly, we're going to look at the area one now. The area one, remember, you need to take the scale factor and you need to square it. So in this case, notice I'm going from 10 to 5. So my scale factor from the from the bigger one to the smaller one is 5/10, which is 1/2 or 0.5. So I would just need to cut these things in half to get my new. You just leave it there. Thank you. It's fine. I'll know it's yours. Thank you. Just when you thought you had him out of your mind, Hayden Zimmerman comes back. Anyways, so since I'm getting smaller, I'm cutting each of these in half to get this one. So it's going to be a similar thing with the area, except I'm not just going to cut my area in half. It's not as easy as perimeter. I can't just cut 36 in half and be like, ooh, half of 36, 18. Area of this one has to be 18. No, because remember, area is in square units. So since the scale factor is 1/2, what I'm going to do is I'm going to take 1/2 and I'm going to square it. 1/2 squared is 1/2 times 1/2, which is 1/4. So I'm not going to take this thing and cut it in half. I'm actually going to take this area right here and cut it into fourths, or divide it by 4. 36 divided by 4, or 36 times 1/4 is 9. So actually the area of triangle DEF would have to be equal to 9 square centimeters. Okay. So there's a lot thrown at you. We want to make sure that you get the notes down, have some examples in, and we will do some more examples in class here as we set up ratios, set up proportions, and solve for missing values. So good work, and we will see you in class. I don't remember how to stop it. So I'm going to keep hitting buttons until it stops. Yep, still don't know how to stop it.